thanks very much for the introduction, and thank you everyone for still being here after a long afternoon, knowing that there won't be another tea break. So today I'm going to focus on, well, I'm press the button. That's the one. Oh, always give me that. Yeah, everything's fine, yeah? Okay, cool. So today my topic is microscopic three-dimensional imaging photonic structures. Right before I start, I want to give you a few ideas. Say what I want to say, or what I want to talk about, or what I trying to avoid to talk about. I'm very happy just realize my talk have some kind of overlap with the previous talk. I'm quite pleased with that because it helps me to explain some concepts. So I'm trying to avoid maths. I'm trying to avoid like some technical terms. I'm trying to give you. I'm trying to show how how beautiful is the world under microscopes, and I'm also trying to give you a bit information about the applications. Oh, if I move along, oh, I can press that.
I think that's pointed.
So okay, I'm going to press the button, right?
Yeah.
Okay. Okay, so I start with my talk with a question. So what do I mean by photonic structure? To speed up. So the photonic structure I mean is the photonic structure of photonic devices. They are, as mentioned in the previous talk, they are going to replace semiconductor devices, and they are expected to rise and compete with them to first to form some kind of hybrid devices, then they expect to completely take over. And so what is photonic device? So can I give a definition? Yes. Oh, I can give an example. So optical fibers, as everyone quite familiar with, they are one type of photonic devices. If I can give a definition, just as you heard from previous talk, they can be compared with electronic devices, especially the relation between photonic devices compared to light, to photons. They can be compared with electronic devices to electric current and electrons. Okay, so what's my role? What I'm trying to do? I'm trying to help to by the end of my study, I'm trying to help. I'm aiming to provide some useful tools for the people who develop who trying to develop the photonic devices and my tool is mainly an imaging tool. Okay, second question. So what kind of photonic devices do I want to make functional? I want to answer this question by three papers. So it's one paper on the left and two papers on the right. On the left, I'm going to spend a little bit more time on this slide. So on the left, this is the first paper. This is the paper first report. Like this is the paper first report is one method of creating a refractive index change in a transparent material, and this change can be used to make what we call channel photonic waveguides. So obviously, the photonic devices I'm interested in, they are based on channel waveguides. To give you a bit more idea, so in the previous talk, you heard about the optical switch. This one is more about like optical wires. So this method first reported in 1996. They use 50-second ultra-fast lasers, and they focus in the transparent material, and then by translation of the material, then they can create lines. And essentially, those lines are uniform change of refractive index. this is okay. So this is 20 years ago, and then there's two paper, one figure from one paper, and another figure from another paper. They are randomly selected from next year. So they kind of like a standardized procedure to report the progress on this fabrication method. How do they report the progress? Is on the left they use transmission microscope image. Just as this image, they report, okay, we made some change here. And then again, there's another transmission microscope image. We made some change here. And on the right, this image, what we call near field profile image. Essentially, this image want to show, okay, our device is functioning, our device is working because light can go through, and that's the light you see from one. That's the light profile exited from one end of the waveguide. Okay, so I'm not quite happy about that because I believe this image method can be improved. As you can see, when I present this figure on this screen, you can actually see nothing there. But if you look carefully, there's four slightly dark region in the middle. Again, in this photograph, they're not trying to show this dark region. What they're really trying to show is some region in the center can guide light, just as you see from this image. But you can't see it there. You can't even see that in the paper. Why is that? So I'm going to answer that in my next slide. So why it wasn't visible? Or can we use kind of three-dimensional image method to visualize that? Okay, on this slide, I'm trying to answer why it wasn't that visible. So the 2 points I want to emphasize on this slide. One is the transmission microscope image. They are not suitable for what I call here phase optic. It's a term. Waveguide, refract index change, uniform refract index change in a transparent material. They are phase objects. Our eyes, camera, like the conventional cameras, they're not sensitive to phase change, so we can't see them. And so one way of seeing them is this is the in focus image, as you can see. You can't see them, literally nothing's there. And one way of seeing them, very simple, trying to defocus a little bit. Okay, you can make them visible. That's what they have done. They didn't mention that, or they probably didn't realize they have done that. But it's not a good way because you lost your resolution is worse, and you don't know the relation. This is not a linear relation between this size to the real size of your devices. And here on this movie, again, same microscope, just as what you have used in secondary school in the biology class. What it's doing is stepping down along the z-axis. So it's moving. You're moving your objective lens down, and then you focus into different plane. If you from biology, if you have used some like very expensive microscopes from a biology lab, then you probably know one way of creating a three-dimensional image is taking multiple images and then build them and then reconstruct them as a three-dimensional stack. So if you are from a mechanical background, then you will be familiar this way of presenting three-dimensional structure as orthogonal view of three-dimensional. So what I'm trying to show you is, so here is your XY plane, and here is the Z plane. Here's X and Z plane. Then and I have a cut as indicated by this yellow line. What I want to show you here is, as you can see for this spot, on the XY plane, it's in good focus because, well, here you have that yellow line right in the middle of Z. So that's where your focal plane is. But we're kind of expecting, because this yellow line here and also that yellow line here also cross this spot, so we also expect this region is in good focus, but they are not. Why is that? Well, this is not something new. This is like studied 30 years ago, very well studied by some researchers, like in 1985. So they have done many theoretical analysis. So, if I explain this in a very short word, it is because when you're looking through from the side, they are blurry because you not isolate this. You not isolate your light. So when you focus here, light from above, light from other planes, they all come into your camera. That's why you can't. That's why they're blurry. That's why the contrast is bad. So, well, as I said, they not quite work. So how can I make it work? Here, I want to give you a quick show in the same project, same specimen. I want to give you a quick taste of what it looks like under a three-dimensional microscope. Here again, this is transmission microscope image, and in comparison, what I have is what we call THG's third harmonic generation microscope. This is rather complicated microscope. It uses nonlinear property of laser, and it's one of the scanning laser microscopes. As you can see, the contrast is a lot better because as autofocus light autofocus light is not creating any signals. That's why the contrast is good. And also you can see the profile along Z. So the profile along Z, they are also a good sphere, as revealed by this image. Again, another one, as I said, I want to show you quite a few colorful, pretty worlds under the microscope. Again, another sample which you can have limited information acquired from this transmission microscope image, whereas from this third harmonic generation microscope image, it look quite striking, look quite impressive, where you can reveal all the details, even within inside of this layer. Something I forgot to mention is the reason why the mechanism why the contrast is generated is for this type of microscope, we believe the contrast is generated and the interface between different refractive index. So that indicates outside of this sphere you have one refract index, and inside you have another refract index. So whenever there's a refract index change, whenever you get contrast, whenever you get signal. Okay, here I want to show you a simpler microscope I built, which also has three-dimensional imaging capabilities. Here's a photograph of our optical table. In the green circle is, as I said, it's our local fabrication facility, similar as the paper in 1996. And in the right circle, I have a built-in confocal microscope. Some of you probably have heard of this kind of microscope if you visited some biology lab. Here, this diagram probably can re-emphasize, can repeat my what I was trying to say. Why conventional transmission microscope didn't work for three-dimensional images? Because here, this dashed line, they are in focus plane, and the green light from this plane, they are they goes into the here I have a PMT photon multiplier tube. It's similar to CCD camera. So it goes into the camera, forms good image with the best resolution you can get. But without this pinhole, imagine you don't have this pinhole here, then the green light, the red light from another plane, which is different from the in-focus plane. They're also going to go into your detector. That's where your blurry comes from. That's why you couldn't have a good three-dimensional image. So confocal, what it means, it have a pinhole here. So essentially, you have another focal spot here, which is conjugate to your focal spot here. So that's why it's called confocal. You blocked out your autofocus light, so you only have the in-focus light there. You greatly increase the contrast. Also, more importantly, give you what we call sectioning capability. You can see it. You can have the resolution along that. Right. So that's a simpler diagram. This is a diagram with a little bit more details. Also, one thing, if I can mention, is so what's unique in our lab is we always have something like a deformer mirror or other devices where we can manipulate the phase profile of the laser, so that we hope that can do many things. Because it can, as in previous slide, you probably have heard aberration correction, those kind of functions. Okay, some more images. Again, third harmonic generation image, and this is and on the right you have image acquired from the previous confocal microscope. So this verify. So these are two different. These are cross section of the waveguides. Two different type. One, as you can see, relatively circular. The other one is elliptical, and this result verified by the confocal. This observation. Rather than I show you what the deformer mirror can do. It can give some image enhancement. So this is as you use a flat mirror, and then as you can see the image quality is not as good because you used a different mirror, and after you train your mirror, you mirrored your phase map and you correct your aberration. It removes the aberration and give you a much better image quality. Right, here's a few more images showing the advantage of using three-dimensional image. Again, this is XY image, transmission microscope image of creature created by lasers, high-power lasers. But you don't know what really happened there. But if you look from the side, if you use the three-dimensional microscope, if you look from the side, so this is XY image. You can see, well, you have some material removed from the surface. So this is on the surface. You have some material removed from the surface. Another one. Again, you have some structure created by the high power laser, and you don't know what happened. By three-dimensional microscope, you can see there are some material. Oh, this one maybe not the best, but also I mentioned for confocal microscope, for this type of confocal microscopes, the signal is generated wherever they have strong scattering and reflections. Last one. So this is application trying to. So both of this are XY image, but upper one is transmission and lower one is confocal. So we have an array of dots where this trying to map the phase profile. But because transmission microscopes, they don't have sectioning skills, sectioning capability, so these dots they're actually on different depths. You can't detect that by a transmission microscope, but you can clearly see that in a confocal microscope. So that gives you the capability capability give you the idea what the phase profile is like for this application. A few more images. Well, as mentioned in previous talks, people interested in wearable electronics, wearable technology product. This is a polymer waveguide. So different from previous images, they're all on glass. So well, glass hard, you can't do anything about it. But polymer soft, you can well, so this group, they have made some prototype where you can wear them. So this is polymer waveguides. As you can see, this is the image supplied by them. But after our three-dimensional image, we have this region of structure which has never seen before. Right. So this is a movie. It's never work. I'll see how many slides I got over there. Okay, not many. I'll skip 2 slides, but I'll show you the movie. Show what it has looked like when the three-dimensional image is reconstructed. So that's how we reconstructed the three-dimensional image, and that's what it looks like. Right. If I close that, if I goes to maybe last slide, I show you what I'm doing in a moment. Okay, again, more polymer waveguide images. Right, here what I was trying to do is because, as I said, waveguides are essentially a change of refract index, but the change of refract index, it can be a step index change. They also can be graded index change. As I said, the THG third harmonic, they only have a general signal and the interface. What if you don't have a clear interface? So that's what I'm trying to do at the moment. I'm trying to use a different method to characterize, to try to measure if the change is not step change. If it is graded, then how can we make sure the measurement of the graded index is accurate? Okay, last one. Let me summarize what we have looked at today. So we, as I explained, the relation between photonic structure, photonic devices. Then I repeat again the perspective of photonic devices against semiconductor devices. I also explained I'm interested in embedding the channel waveguide devices. I showed you what's the additional information provided from 3-dimensional image compared with 2-dimensional transmission microscope image. And last, I showed you what I'm currently working on, refract index mapping, which is done by a combination of previous mentioned methods. Okay, that's the end of my talk. Thank you for your attention and any questions.
Thank you.